All right, so for this lesson, we want to continue looking at area, but this time looking at how we can find the area between curves. And with less of a focus on finding exact values, while quite often we can find those, as we saw from previous lessons, it can quite often add a lot of extra time and work for not always a significant increase in accuracy. So right here I got a shaded region showing that's enclosed between two curves. We have a quadratic function, x squared plus x, that's this right here, and then a cubic function, x cubed plus x squared minus x, that's right here. And so between them, we have these two regions, and we want to find the area enclosed by it. Notice if you look at the question, it doesn't ask for the exact area. And so if this was a test question, you are encouraged to use a GDC as much or as little as you want. And generally, if we do a balance between doing some algebraic work and using our GDC, we can get our answer, correct answer that's quite accurate quite quickly. First thing, what we need here is we need the intercepts between where these two functions cross. I can tell just by looking at it, they cross when x equals 0, but I can't tell where that is or where that is. Well, let's go to a graphing calculator and graph these. And so I have these functions graphed here, and pretty quickly I can see the intercepts here, which are at negative 1.41 approximately and positive 1.41. However, I also want to show you how, in this case, we could actually find those algebraically quite quickly. So because it is quite quick, I'll do that. If I want to find where these intersect algebraically, I just need to make these two equations equal one another. Make this equal this. And as an HL student, we should be able to get this fairly quickly. So I get x squared plus x equals x cubed plus x squared minus x. I'm going to bring everything to one side with the x squared. So I get with the x cubed, my biggest power. So I get x cubed on one side. Minus 2x, x squared plus, I'm getting ahead of myself, x squared, oh no, I'm right, minus 2x. I gotta trust myself a little more. When I subtract x squared from both sides, they cancel out. And now this equals 0. So to solve this, I would take a factor of x out first. So I have x times x squared minus 2. And then analyze my factors. I can see I have one solution where x equals 0, another where x equals plus or minus root 2. And that comes from, again, here. All right, so with that said, the 0 I could tell right away, and then plus or minus root 2 are just more exact values for x in terms of where these intersect. So I'm going to label these on my graph. So the 0 I knew already. This one is at negative root 2. This one up here is at positive root 2. All right, so how can I find now, I got the intersection points, the area here? Well, the part that I've highlighted in yellow, notice this is where my cubic function is above my quadratic function. That means in this region here, my cubic function is greater than my quadratic function. So to find that area, I need to find the integral of the cubic function, and from that subtract the quadratic function. And so that part highlighted in yellow can be expressed with the integral from negative root 2 to 0. That's why I needed those intersection points to know where the bounds of this integral was. The cubic function, which is in this case the larger one, which is x cubed plus x squared minus x. All of that minus the function that's less than it in that region, which is the quadratic one, x squared plus x dx. Keep in mind at this point, I could just deal with this right now. I will collect like terms here. So I get the integral from negative root 2 up to 0, and it simplifies to x cubed minus 2x dx. And at this point, I could solve this exactly using antiderivatives, but again, it doesn't say I have to have an exact value. And so I'm definitely going to use a GDC here. It's extremely quick. And we get actually exactly 1. Because I'm using exactly negative root 2 in my bound there. So that area in yellow has an area of 1. So now I want to do something similar for the area in blue. This time it's the other way around. The quadratic function is greater than the cubic function. So I want to integrate this the other way around. And so over here, I want to find the integral from 0 up to positive root 2. This time, though, I want to start with my quadratic function, x squared minus x, and from that I want to subtract the lesser function at this point, the cubic function. When I collect like terms, which I don't actually have to do, but why not? I get the exact same function before, both opposite signs. I have minus x cubed here. I have plus 2x dx. And again, I can use a GDC, and again, I get exactly 1, which means these two regions, while they're different shapes, have the exact same area of 1 each. So put it all together. It looks kind of like a cat right now when I draw it like that, but put all the area all together, I get 1 plus 1 equals 2, and there's the area. That total area is 2. Now, there is another approach that's even faster using my GDC, which I'll actually mention for the next question. But in this case, notice I did a mix. I used algebraic work to pretty quickly find my x-intercepts in this case that are exact, but I use a GDC to do the more mundane work of finding those finding the integrals. Although it wouldn't be that hard to find the antiderivatives for a polynomial function. So for this, I have something, again, similar. I want to find the combined area of these two shaded regions. This time, what looks like a linear function is a logarithmic function. That's the natural logarithm of 5 minus x. And then I have this cubic function. So again, no matter how I want to solve this, I need to find my intersection points. In this case, I can't really tell any of them just by looking at the graph. So I'm going to graph these two things using a GDC. And I see this, okay? Now keep in mind, I'll adjust my scales a bit, but I'm just paying attention from this intersection point to this last intersection point. So these three I'm gonna write down, although in the end I won't actually need all three, but the x values of these intersection points tell me where the bounds of these shaded regions are. So I'm gonna copy these down to a fair amount of detail because I don't wanna round to 3 significant figures yet and then use those values. So basically just copying what I had on there. That point there was at approximately negative 3.84158. This point here was at approximately negative 1.2964. And this point here is at approximately positive 1.12444. All right. So to find the area of this, I can do the same thing as before. I can find the area of this region, which is where my cubic function is greater than the logarithmic function. So I'd find the bound from negative 3.8-ish to negative 1.3-ish. Those would be my bounds. I go the cubic minus the logarithmic, and then I'd have that area. I could then do the same thing for this region, except this time my logarithmic function is greater than the cubic function. So I do the same idea with different bounds. At this time it would be the logarithmic function minus the cubic. You may look at these and say they're the same and therefore double it, but I don't actually think they're exactly the same, so I wouldn't take that risk. In fact, I'm pretty sure they're not exactly the same because that logarithmic function is not a line. It's not a horizontal line cutting these. However, a faster way is I can find this whole area by just finding the integral of the absolute value of this difference. And so let me show you what I mean. And so I can find the integral from just the very beginning point to the very ending point. So like I mentioned before, I don't really need that first point. And so I'm going to go from negative 3.84158 up to 1.2444. But of the absolute value of one function, take away the other. And since it's absolute value, it doesn't really matter what order. I'm going to go cubic minus logarithmic. So my cubic function, x minus 1, x plus 1, x plus 4, minus the natural logarithm of 5 minus x. So the absolute value of all of that dx. Keep in mind everything we see here, the cubic function minus the logarithmic function. When the cubic function is larger than the logarithmic function, then we're going to get a positive number anyways. However, in the secondary region, when the logarithmic function is when the cubic function is less than the logarithmic function, then, well, we'll get a negative number, absolute value, make it positive. So this kind of takes all that to account. And so that is pretty quick. If we're doing this, we're using a GDC, but it's not asking for an exact value. And so I would type this in, and it should just take a few seconds, and you should get approximately 19.1 square units. And so I could have done the same idea for this previous question. I could have, instead of breaking it up into 2 regions, I could have found the absolute value from the first intersection point to the last intersection point of one function minus the other. Again, the order I subtract them doesn't really matter because that's absolute value makes everything positive. All right, for the last one, I'm now looking at the shaded region kind of to the left and right between functions. And if I look at my equations, the graph in blue is not solved for x or y, it's x plus y squared equals 4. And the graph in red is a line as x plus y equals 2. So to find this region, we have a few options. One thing we could do is we could take this function here, solve for y, and if you solve for y for x plus y squared equals 4, you quickly get the y squared equals 4 minus x. Square root both sides, you get y equals plus or minus the square root of 4 minus x. So that tells me that this here is the top half and the bottom half of this curve. You can imagine the plus root 4 minus x, that's the top half. The minus root 4 minus x is the bottom half. And so, well, I'll label that. I also don't want us to think that is actually going to be terribly helpful, but it's not wrong, and so I'll label it. And sometimes we're just used and we like to see things solve for y. So this is root 4 minus x down here is minus root 4 minus x. The x plus y equals 2, that's very easy to solve for y. You just get y, subtract x from both sides, y equals 2 minus x. And so one advantage of doing this, if you do actually solve for y, is at some point we need to know the intersection points for these. And while we could solve this algebraically, I could isolate a variable for each and put these together, and we should be able to algebraically solve for x and y quite quickly. We also could just graph now 3 functions. We'd have to graph this, this, and this, and you should be able to see where they intersect. So it's a matter of opinion what's faster. If you're pretty strong with your algebraic skills, which you really should be at this level, it's probably faster to solve it algebraically. Either way, though, I will jump to a graph. And we should see something like this. I'll adjust my scales a bit. And I need to know where they intersect. So they intersect at 0, 2, and 3, negative 1. So I'll label that on here. That's the most important part. So 0, 2, and 3, negative 1. All right. That said, one option is I could find the area of this region here, which would be the root 4 minus x minus the linear function. And then I'd have to do something similar for this. However, though, what would be actually much more convenient in the end, although it may seem kind of strange, is to think about inverses and think about functions solved for x instead of solved for y. And think about the integral with respect to dy instead of respect to x. And essentially, I'm looking at everything the other way around. Now, if I turn my screen around, it doesn't make a difference for you. But if you have this on paper and you rotate your paper 90 degrees, you have your x and y axes kind of look swapped around. And essentially, we're looking at the inverses of these. And so this is a really important idea that is the whole point of this question to introduce. And so for this, I've already found the intersection points. But now I want to think about a couple of integrals. I want to think about the integral in terms of y, from the lowest bound on y up to the highest bound on y. And so I want to think of an integral from -1 up to 2. And I want to think about this function here, but in terms being solved for having x isolated, or having it be a function of y minus this function here. But again, having my x and y swapped around. And so before this gets too messy, let's pause actually this part. Let me move this down here. And let's solve for x in each of these questions. And we're always used to solving for y. And so if I take this here, it's actually quite nice to solve for x. You subtract y squared from both sides, and we get x equals 4 minus y squared. And for here, if I solve for x, I get x equals 2 minus y. And so I want to imagine this function here minus this function here. And so in terms of y, I'm looking at a lower bound of -1 up to a higher bound of 2 of 4 minus y squared minus 2 minus y. Because again, I'm thinking about moving along the y-axis instead of x-axis. And if you didn't realize you can do that, you can do whatever you want, right? We tend to start with, just like with derivatives, we tend to start with dy over dx, but it doesn't have to be with respect to x. So in this case, I am finding the area, really, of all these little infinitely thin rectangles moving my way along the y-axis from -1 up to 2. If I'm doing that, then it's not dx here, it's dy. And that there is the fundamental new part. Now, at this point, I can collect like terms pretty easily. It is optional, but if I collect like terms, I get just 2 minus y squared plus y dy. And I could solve this algebraically, but it'd be quite quick to solve this using our GDC. Now, in your GDC, you'll probably be easiest just to replace those y's with x's. But again, that's just a matter of using your GDC. But that should be fairly quick. And we should get an area of exactly 4.5, actually. And so keep in mind, this idea of finding an integral with respect to y allows us to think about, instead of the areas, for example, here, instead of imagining us finding the area working this way, which is what we've always done in the past. So this is as our dx's as we move up the x. If we have it in terms of dy, then it's going like this, which, even though it may be new, I hope that idea makes sense instead of we're swapping around our variables. That said, there's always lots of options, but we definitely now need to start being open to the idea of integrating with respect to y instead of just with respect to x.